frequency. We all know wherever we have a mass and a stiffness, there is a natural frequency, which means this is root k by m, if we know by from our subjects, that anything from earth to the last atom, we have a natural frequency associated with it, which means if this is a slab area that I am standing on and this has a typical mass and some stiffness connected to it, this has a fundamental natural frequency that it gets excited easily. Even a single tap of it, the whole floor may be vibrating. I may not be able to see it, or I may not be able to quantify it directly, but it is doing that, and this is true to any object around. So for some reason, if the excitation happens to be of the same frequency, for some reason there is a truck moving there, it has got a rotational frequency of the wheel which matches with the natural frequency of your system. Obviously and for sure, even though the excitation value is small, because of the tendency of natural frequency and resonance, the effect of natural frequency getting coincided with the excitation makes it go to a condition called resonance. And resonance, we have all different words. Most of us know about the Toyama bridge that fell off. It's a one classical case of aeroelasticity failure. People say wind induced it, but there is a motion which is uncontrollable, damping failed, stiffness reduced, all are connected. Finally, the structure went through a catastrophic failure. So I'm not making a scare show here in the sense that all buildings are going to fall down. There are experts here who know civil engineering, but what we are trying to bring in is the relevance of vibration into structure, how to know it upfront, or can we take some considerations during the design stage. If we are not yet ready there for the design or upfront consideration, there is a lot of methods to do post-investigation, check for vibrations, quantify them, go with the standard which clearly defines what is the room, and then look for the remedial action. So here in the fourth and fifth step, selecting feasible vibration mitigation plan, it is not limited to one kind of material, one kind of way of looking at a problem. With doctor's guidance, we have done work in Volvo.
That you can make use of the cursor itself. That doesn't work.
Sir's help, we have done a project in Volvo here in Bangalore campus that I can, instead of going to case study, I can tell it right away. There's a earth compacting machine in Volvo. They do this as a compactor. So this machine is, if you have seen this these days, you don't see a road roller on the road, which is a static rolling machine after the asphalting is or the tar is put. It's not a static roller. It's a dynamic compression that it does. And depending on the type of work, type of compression required, type of compaction required, this machine's frequency can be controlled. Typically what I'm trying to say is, there are two rolls which are hydraulically controlled, and they can oscillate at a particular frequency, making the compaction easier, better, technically superior. So if that is the scenario, they have to be done and tested at the manufacturing facility. Here is the case of Volvo. They have a small foundation or a test area. The Volvo's business strategy changed and their test area was to be moved to the front side, if I'm correct, sir. So they were all hiding at the large campus they have in Pina, but they were to be moved to the front area of their campus, and they didn't know what is happening later. So they moved this testing facility. The testing is just 30 seconds, believe me. They start this machine, it vibrates vigorously starting from 0 hertz. This 0 does not exist. Starts from the least possible frequency, goes just up to 30 cycles per second, and the testing is only 30 seconds. You know, the adjoining, there's one 30 feet road, and then adjoining building belongs to